So the first question is, did anyone notice the deliberate error right at the beginning of the last lecture? Came from the internet. So I told you about the second biggest black hole in the Milky Way, and I showed you that picture. Okay, so there was an error. Actually, I only noticed it afterwards. The Guardian said that the black hole in the center of the Milky Way is 400 million solar masses. Okay, actually, this is an error. It's 4. Okay. So they did correct it yesterday on the Guardian website. The most massive one is 4 million. I don't know where the 100 came from. And the second most massive one is, whatever they claimed it was, I hope, some number of 100,000. I don't remember. 200,000. Okay, so that was a mistake. Just should be a warning. Don't believe anything on the internet to a first approximation. And secondly, don't believe anything I say. All right. So just to remind you, as we discussed last time, we can condense Maxwell's equations into 2 equations if we combine the electric and magnetic fields into a single object, this antisymmetric 4x4 matrix. We call it a tensor because it has a number of indices. And the electric current density and the electric charge density are combined into a single object, the 4 current. This is also called a 4 current. It has 4 components. And the equations become this. So we're going to well, as I mentioned, these are really the basis for the theory of relativity, and we're going to see exactly how now. So let's try and get this in the right order. There we go. The second equation looks a little complicated. Let's call this one 1 and that one 2. So we can, 2 also implies the following, that dl. So you see, what I've done with 2 is just cycle the indices. So I've moved the second one to the first, and the third to the second, and the first to the last. Right? So this is this quantity plus cycles. This one I've shifted everything by 1 and rotate this around, and this again. You can rewrite equation 2 as follows. Like this, equals 0, where that notation means anti-symmetrize. Okay, so what does that mean? Obviously, if I take a tensor, A alpha beta, and I try to make it anti-symmetric on those 2 indices, what I do is take 1/2 of A alpha beta minus A beta alpha. Okay, so any tensor can be decomposed into 2 pieces, and any symmetric tensor. Any 2-index tensor can be written as a sum of 2 pieces. An antisymmetric piece, where I flip the indices and put a minus sign, and the symmetric piece, which is written with round brackets, A alpha beta plus A beta alpha, And then obviously it's true that A alpha beta is the sum of the antisymmetric part and the symmetric part. Alpha beta. Okay, so this procedure of symmetrizing and antisymmetrizing is often very useful. The reason it is useful is that when we consider the transformation properties of A, how it changes under the symmetries of the theory, we'll see the symmetric and antisymmetric parts change in exactly the same way. So what do we mean by this? Where I have three indices, if I have some object with three indices, okay, the generalization, which I've already hinted at, is to put 1 over 3 factorial and then do all the permutations of these indices with a plus sign if they're even number of pairwise flips, and a minus sign if they're an odd number of pairwise flips. So this becomes alpha, beta, gamma, and then I can obviously I can flip beta and gamma and leave alpha where it is, right? Or I can put, well, let's just write it this way. We'll put either the alphas first, or the betas first, or the gammas first. And in each case, we'll get one plus sign and one minus sign. Okay? So if the beta is first, then this should be gamma alpha. Okay? And if the beta is first, this should be alpha gamma. Right? Is that clear? Because when I flip the beta with the alpha, there's only one flip, so I get a minus sign. And then the if the gamma is first, I get alpha beta and beta alpha. Sorry, that doesn't look right. That's wrong. That's gamma beta, right? Alpha, beta, gamma. Then if I flip the beta and gamma, I have a minus sign, right? Is that clear? Okay. And obviously, if I have the symmetrized one, then I just have pluses everywhere. Okay, so let's just verify this. Let's write this out. So d alpha f beta gamma plus d, this is minus d alpha f gamma beta plus d beta f gamma alpha minus d beta f alpha gamma plus d gamma f alpha beta minus d gamma f beta alpha. Okay, but by the antisymmetry of f, each of these terms, this term is just the same as that one, and this term is just the same as that, and this is just the same as that, right? So that's equal to twice the alpha f beta gamma plus cycles. Okay, which is 0. Okay, and the reason for writing it like this, it looks a little clumsy at this point. Why introduce all this notation? The reason for that is then we can write two as epsilon alpha beta gamma delta d beta f gamma delta equals 0. Okay, so the epsilon is this totally antisymmetric tensor, which exists in 4D just like it does in 3D. And if I, because it's totally antisymmetric, this is automatically going to project this 3-index quantity only onto its antisymmetric piece. Right? I can, and so this is equal to epsilon alpha beta gamma delta d beta f gamma delta antisymmetrized. Okay, which is 0. Okay, so Maxwell's equations, the second equation is just this one. Now, having done this, it's having rewritten the equation this way, certain things become easier. For example, let's just take the d gamma of equation 2. Actually, I'm going to take it in that form, in the form up there. We call this 2 prime. D gamma of 2, and you can see immediately that the first term and the second term involve, so this is d alpha f beta gamma, but now I've got d gamma. This gamma is, this derivative is acting on that gamma index. I'm free to lower this one and raise that one, right? That's the same thing, because remember, if I have A alpha, B alpha, what is this? This is eta alpha beta, A alpha, B beta, because you raise and lower indices with the eta. And that's equal to A alpha, B alpha, because here I have B. I've got my indices. Sorry, I want that one. Sorry, I'm getting all mixed up. Alpha beta. And so that's the same thing as A beta, B beta, right? Because I raised the index on the A and contracted. So, but we have that d gamma on f beta gamma is, of course, minus d gamma on f gamma beta, which is 0 by 1. So the first term gives 0 because the gamma derivative acts on the f beta gamma. The second term likewise gives 0, d beta, d gamma, f gamma alpha. So this is 0, this is 0. And then we have d gamma, f alpha beta. That should be 0. Well, this is just the wave operator. Okay, so in this form, it's a little bit easier to see that the field strength, the electric and magnetic field strengths in the absence of, this is for j equals 0, sorry, if j equals 0. The electromagnetic field strengths obey the wave equation if the charge and current densities are 0. This is obviously only true if j is 0. Okay, now another way to think of this equation, and this equation too, why this is one reason why it's useful to write it this way, is or 2 prime, is that this means that the 4 curl of f gamma delta is 0. Okay, so you know in 3 dimensions, if I have the curl of a vector, A equals 0, what does that tell you about A? If I have some vector, which is a function of x, right, and its curl is 0, what does it mean about A? It's a gradient, right? And you know how you prove that? You use Stokes' theorem, and you say, you use Stokes' theorem, and then you define phi, some gradient, to be integral of A dot dx along some curve, C, to the point x. Let's say you have some x naught. Okay, so that defines phi, but and along some curve C. But this is only integral along some curve C. Let's I don't know, write it that way. This is only meaningful if the function is independent of the choice of curve, right? And that is true because if curl is A is 0, that means that integral A dot ds equals 0 along some through some sorry. If curl A is 0, then the integral of a closed loop, the integral around a closed loop of A dot dx equals 0, because by Stokes' theorem this is proportional to integral curl A ds, where ds is this area. Okay, so then this becomes a well-defined function, and then obviously with this function the gradient of phi equals A. So I'm not going to prove that in 4D, but the same is true in 4D. It's just harder to picture. So if and the curl involves this epsilon symbol, so if the curl of f gamma delta is 0, this implies that f gamma delta is equal to the gradient of something, and it's antisymmetric, so it must be written this way. Okay. So this is called Poincaré's lemma. So this implies f is the gradient of something, and this this is Poincaré's lemma. And in this case, it implies that f can be written in that way. So because this equation is true even if there are currents present, and basically this equation comes down to the statement there are no magnetic charges and currents, right? Because over there was really the electric current appeared on the right-hand side. This should be the magnetic current. Since there are no currents, since there are no magnetic charges and currents, it's possible to write the field strength as in terms of the gradient of something. And so in particular, let's consider we're going to write this quantity A as phi over c and vector A. And you'll see why I put the 1 over c there in a moment, because now we're just going to recover the usual formulae from electrodynamics that Bi, which is 1/2 epsilon ijk fjk, is 1/2 epsilon ijk dj ak minus dk aj. Now, since the epsilon is antisymmetric, and this is antisymmetric, we need, since the epsilon is antisymmetric, we need to keep only one of those terms and lose the factor of a half. And so and this implies that obviously B is curl A. Okay, so if you remember your electrodynamics, we frequently use this formula that it's possible to write the magnetic field in terms of the curl of a vector potential. And so the only difference in relativity is we have a 4-vector potential. And what about the phi? Well, we just do the same thing with the electric field. The electric field, which is from that formula up there, the electric field is F0I. Let's put a C somewhere, E over C. And this, you can check, implies that the electric field is minus the gradient of phi, the usual expression, minus dA dt. Okay, so often in electrostatics we just use this part because d by dt is 0. But in general you have to write the electric field in terms of the time derivative of the vector potential as well as the gradient of the scalar potential. Okay, so that's just to explain a little more how this recovers everything in electrodynamics in a more elegant way. You'll also notice that if we replace that A is not unique, A alpha is not unique. Right? If you write, let's go back to this case. If I want to write the vector A in terms of phi, obviously there's some ambiguity in this formula because the x naught was arbitrary. Right? And clearly if I change phi by a constant, A is unchanged. Well, in electrodynamics, that ambiguity gets bigger because if I replace A mu with A mu prime, which is A mu plus the gradient, the 4 gradient of any function on space-time, then this implies that F mu nu prime, which is d mu A nu prime minus d nu A mu prime, equals F mu nu, coming from this term, and then plus d mu d nu minus d nu d mu f, and this is 0 because partial derivatives commute. Okay, so the many different choices of 4-vector potential give exactly the same field strength. Okay, so this is called gauge symmetry. And the choice of which particular A you choose to represent a given electromagnetic field is called the choice of gauge. Okay, and this was realized late in the 19th century that in electrodynamics it was very convenient to introduce these potentials, phi and A, but it was also realized they are not unique. This gauge symmetry then became a more and more fundamental notion in physics, and now the whole of the Standard Model is built on the idea of gauge symmetry. Okay, and in fact, there's a very interesting relationship between general relativity and gauge symmetry, which will shed further light on this. So at this point, it's a little mysterious. Why is it convenient to write nature in terms of variables which are not unique. Okay? But this is actually everywhere in general relativity. In a sense, nothing you write is unique. Almost nothing you write is unique. But we'll come to that in a moment. Or to say it even more physically, this quantity, a mu, cannot be physical. Because if I change it, it gives the same physical fields. So why is it useful to have it if it's not physical? So it turns out this is endemic in physics. It's very, very useful to write things in terms of variables which are not physical. And we're going to see more and more of this in the course. Okay, so any questions? Yes?
Is A completely unphysical? Or is it
No, not at all. No, because the one way of saying it is in order to do calculations, it's very convenient to have A.
Yeah.
At the end of the day, when you want to relate your calculations to a physical process, the only thing physical is F.
Yeah, I mean, is
Okay.
there something more in A that you don't see just from F?
Actually, there is. That's a great question. The answer is classically not, but quantum mechanically there is. And this is called the Aharonov-Bohm phase, but that's only the beginning. Okay? So essentially, one way of saying it is that the only thing you could ever measure locally would be the field strength, electric and magnetic field. I can go to some point in space with a little magnet, and I measure the magnetic field. And likewise, the electric field. Okay? But there are situations where a particle can traverse some curve in space and come back, and there was zero electric and magnetic fields everywhere along that curve. But the particle that has traversed this curve is different than the one that stayed there. And that's a non-local effect, which is called the Aharonov-Bohm phase. And actually, we can see that because the Aharonov-Bohm phase is defined to be the integral around a closed loop of A dot dx. Okay? So I think about this as a fixed moment of time, or if everything is just independent of time, and I integrate around a curve. And then obviously, if I do the same with A prime, where A prime is changed by a gradient, okay, then the integral of the gradient around a curve, what does that measure? Well, it's just the change in the field, right? So if I integrate a gradient around a curve, what I'm going to get is the two endpoints of the integral, which are the same. Okay, so as long as the phi is single valued, if I integrate its gradient around a curve, I'm just going to get 0. So this is 0. So actually, non-local quantities involving the vector potential can be gauge invariant. And those can be physical. And they are physical. But the only way to measure these things is using quantum mechanical interference. Okay, so this is very interesting. And when we get to general relativity, we will see the analog of these gauge choices is the choice of coordinates. Right? If you ever want to describe geometry or space and time, you have to use coordinates. We don't know any other way to do it. We would love to describe space-time without coordinates, but we don't know how to do that. So I have to introduce these coordinates, but we know these coordinates are just completely artificial labels. Right? I choose this point to be my origin, and I can just lay down any set of coordinates I like. And in fact, general relativity, the fundamental principle, is that any equation you write should be valid in any system of coordinates. Okay? And so that's the gauge freedom. It's a very, very big gauge freedom. Freedom to change coordinates. And then all physical quantities which are local have to be independent of those coordinates. But there's some quantities which are not local, which are also independent of the coordinates. And those are more subtle, and those can be measured in quantum experiments.
But shouldn't we have already these gauge symmetries of coordinates already in classical mechanics or any type of physics? Because usually we want
it's
it
true.
to be coordinate independent.
Yeah, it's true. So GR is completely classical, right? So, yeah. So, indeed, coordinate freedom is there in classical mechanics. In GR, it sort of rises to a new level because, well, we'll get to that. We'll see in special relativity we have a restricted set of possible coordinates. In general relativity, we're allowed to choose any coordinates. Okay, so let's continue this theme, but it's good that we're already making connections which are useful. So the analog, or let's say this will generalize in general relativity to the freedom to choose coordinates. Coordinates on space-time. So again, the sort of hint was there in Maxwell's equations. By the way, Maxwell's equations have a huge amount of symmetry. As kind of trivial as they look, they contain the seeds of all of 20th century physics. Right? So they have Lorentz symmetry. We're going to do that right now. They have gauge symmetry, which gave rise to particle physics. They have another symmetry. Do you know what the other symmetry is? Conformal symmetry, symmetry under changes of scale. There's no scale in Maxwell's equations. So they're kind of a seed of many of the revolutions in 20th century physics. Okay, so now we're going to go to Lorentz transformations, which are the coordinate transformations which enter into special relativity. So as you pointed out, in classical mechanics, we have some freedom to choose coordinates. We write, e.g., mx, Newton's equation, mx double dot equals minus gradient of v. Okay, so the motion of a particle in a potential is just given by F equals ma, and the force is the gradient of some potential v of x. Now, obviously, in writing this down, we use some coordinates for x, but there's nothing special about any particular coordinate system. I mean, I can measure my coordinates from the corner of this room. I can measure x, y, and z, or I can choose the other corner, or I could rotate the room. There's a lot of freedom in the coordinates. Okay, so the coordinates x are arbitrary. And the equation is invariant under x goes to x prime, which is some matrix multiplying x, a rotation matrix, where O is a rotation matrix. Okay, so what is a rotation matrix? A rotation matrix is a matrix. I guess sometimes people write a double bar under the matrix. It has components which satisfy a rotation matrix O satisfies O transpose O equals 1. And the reason we define things that way is that this means that distances and angles are invariant. Okay, so what is the distance? Well, let's measure the distance of something from the origin, x squared, so that's xi, xi. And if I prime it, that is oij xj, oil xl. But if O transpose O is 1, that means that OIL, let me write it this way, O transpose, OIL OJL equals delta IJ. Okay, because matrix multiplication, you have to sum over columns and rows, but this, of course, is O transpose LJ. Okay, and so in this case, let me see. Actually, I did want it the other way. I wanted it this way. Sorry. So I want O transpose IL OLJ, and this is OLI OLJ is delta IJ. And so you see what I'm doing is summing over the first two indices, and the other two indices are free. And so here I've summed over the first two indices, and these two indices are free. So this is delta JL xj xl. So that's x squared. So rotations leave distances invariant, and that's physically obvious. That if I rotate something, its length doesn't change. And similarly, if you take the angle between two vectors, take their dot product, and you rotate the vectors, that doesn't change either. And that's just because x dot y is unchanged under rotations. Okay. Now to come back to this equation is unchanged under rotations, because if I write this down, x prime double dot minus equals, well, let's take everything to the left-hand side, plus grad prime v of x prime. Okay, then x prime is, well, I can write it this way, O times mx double dot plus grad v, and this was 0. So the point is that doing a rotation doesn't change the equation. Okay, the equation in the rotated coordinates is proportional to the equation in the unrotated coordinates, and therefore it's still satisfied.
Why is the rotation special as far as the coordinates are concerned? For example, if I want to talk about polar coordinates,
right,
they are not related to some other coordinates.
No, they're not. They're not.
And it should be still invariant, right?
It should be, but the way Newton conceived of classical mechanics was to imagine was actually based on using Cartesian coordinates, which invented by Descartes, right? Just x, y, z, and t, and these were supposed to be almost God-given, that the world had these coordinates. Now, they were not unique because you could rotate them, and there's a symmetry in classical mechanics called Galilean invariance, and that was based on Galileo's intuition, Galileo's intuition said that rotations or translations should leave the equations invariant, or Galilean boosts, which means traveling at constant velocity. Okay, and all of those are symmetries of Newton's equations. Okay, but that was it. So when it comes to writing those equations in curved coordinates, we do that in classical mechanics all the time, right? And we get these centrifugal forces and Coriolis forces and all that. And all that just arises because it's more convenient often to do the equations in different coordinates. That introduces fictitious forces, right? When you go to curved coordinates, you get fictitious forces. Now, Einstein's amazing insight was the following. What if gravity is a fictitious force? That's it. What if it's somehow more natural to use curved coordinates, and in those coordinates there's a force, and it reproduces gravity? Okay, that was his insight. And so when we think we're being pulled down by gravity on the Earth, the reason is that if I was to look at the sort of natural coordinates, well, we will come to this later. We'll come to this later. But essentially the picture is this. You know, if I stand here, I feel there's gravity. But if I am in empty space and there's no Earth, and I'm sitting in a box, and somebody comes along and pushes the box, accelerates it, I'll feel that there's gravity. I can't tell the difference. And Einstein's insight was maybe that's what gravity is. And the reason that was so deep is that everything falls the same under gravity. Doesn't matter the mass, doesn't matter the composition, everything falls the same. So it was very plausible that gravity is this fictitious force, because then everybody and every object would feel exactly the same force, the same acceleration. So we'll come to that. But for Newton and all the people who did classical mechanics, changing to non-Cartesian coordinates introduces fictitious forces. Okay, and they're willing to live with that. Sometimes it's useful, but that was the first sign, actually, that of the kind of idea that Einstein had. Okay, so rotations are obviously should be a symmetry of are a symmetry, or an obvious symmetry of classical mechanics, and so we write them as x prime I is Oj xj, where this matrix is a rotation matrix, and if I write this equation, OTO equals 1, this defines any matrix which is in O3. It's the group of 3 by 3 rotation matrices. Okay, by definition, they're the matrices satisfying that. They have 3 parameters. It's the Euler angles, and so on. Now, obviously, what we've done is we've changed special relativity, or let's just say Maxwell, the symmetry of Maxwell's equations implies, well, let's put it differently. In simplifying Maxwell's equations, we combined space with time, right? We combined space with time, right? So we wrote x mu is ct x. And all the quantities became 4 index quantities. So it is natural to look for the analog of rotations in 4D. And those are called Lorentz transformations. Lorentz transformations. X prime mu is lambda mu nu x nu. They're also linear, just like rotations. And now we have to be careful about keeping indices up or down. Remember, so we had this, and then we had d mu, which is 1 over c d by dt and grad. And then we have, of course, eta mu nu, which was minus 1, 1, 1, 1. And eta upstairs was minus 1, 1, 1, 1. And we can use those eta symbols to raise and lower indices, and all they really do is make sure that we put minus 1s in the right place whenever we have a time coordinate. So this is the analog of rotations, and the analog of this equation, OTO equals 1, is just that lambda transpose eta, lambda equals eta. Okay, so basically this ensures that x transpose x, analog is. So instead of this matrix delta, you can regard this as an invariance of delta. You can say that O transpose Li delta ij O. Okay, now wait. I think all the indices messed up. I L L M M J equals delta ij. Okay, so you can think about this equation as if there really was a delta sitting in between the two O's. And so what the two O's are doing are conjugating the delta matrix. And the analog in Lorentz transformations is that the Lorentz matrices conjugate the eta matrix. So, but let's start from this, and we'll see all this come out. So Lorentz transformations should be thought of as rotations in space-time, which leave this matrix eta invariant. Okay, so let's start from this equation. X prime mu is lambda mu nu x nu. We sum over the nu. And then it follows that d by dx alpha is dx prime beta dx alpha d by dx prime beta. So this is the usual chain rule. Okay, we're going to use this almost infinite number of times. So make sure you understand this. If I differentiate with respect to some quantity, take the partial derivatives. It's the same thing as differentiate with so what I have here, this this equation just if x prime alpha is a function of x, So we assume that the x prime coordinates are functions of the x coordinates. And likewise, we're going to assume that the x coordinates are functions of the x prime coordinates. Okay, and in fact, what we're going to require is that this mapping from x coordinates to x prime coordinates is 1-to-1. So every point will have some coordinates in x and some coordinates in x prime. But for this purpose, all you need is that x is a well-defined function of x prime, and x prime is a well-defined function of x. Okay, that will essentially require this lambda is invertible. So x prime is linear in x, and likewise x is linear in x prime. But then the chain rule gives us this, that differentiating with respect to x prime and then multiplying by this Jacobian matrix gives us the derivative with respect to x. Okay, so this, of course, is equal to lambda beta alpha. From here, differentiating x prime beta with respect to x alpha, I get lambda beta alpha d by dx prime beta. Okay, so notice that whereas x prime is lambda x, d by dx prime involves the inverse of lambda acting on d by dx. So, i.e., d by dx prime alpha would be lambda twiddle beta alpha d by dx beta. I've relabeled the alpha and beta, and I will frequently do that. Okay, one should always realize that alphas and betas are completely arbitrary choices, and you should always feel free to relabel alpha or beta and beta alpha and whatever you like. Okay, so I will do that just to keep you on your toes. I could have put beta here, but you should realize that you should feel completely free. And these repeated indices are summed, just to remind you. Okay, so where lambda twiddle is the inverse of twiddle alpha beta, lambda twiddle is the inverse of lambda. Gamma equals lambda alpha beta lambda twiddle beta gamma equals delta alpha gamma. Okay, so here all I'm doing is multiplying this equation by the inverse of lambda, and then expressing d by dx prime as the inverse of lambda times d by dx. So in special relativity, we will always be using these matrices lambda and their inverses. And as I said, we're going to assume the inverse always exists because we want the mapping to be 1-to-1. We want both coordinates systems to give for every point a single coordinate. Okay, so likewise, j prime alpha is lambda alpha beta j beta. And what do you think we do for f prime alpha beta? How do I express f prime in terms of f? Okay, so basically you see x has one index, comes with one lambda. An upstairs index comes with a lambda. A downstairs index comes with a lambda twiddle. Here we have an upstairs index. It comes with a lambda. So f has two upstairs indices, so it needs two lambdas. Okay? And this is what you do with rotations as well. In classical mechanics, if you have a tensor, like the inertia tensor of a body, it's a 3x3 tensor. You rotate, under rotations, you need a rotation for every index. And in fact, the epsilon symbol, epsilon, alpha, beta, gamma, delta, right? We needed this in the Maxwell's equations. So how does that go? Well, that is lambda, 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 alpha, beta, gamma, delta, mu, nu, rho, sigma, epsilon, mu, nu, rho, sigma. So that's how the epsilon transforms. And so this is actually equal to, from linear algebra, this quantity is nothing but epsilon alpha beta gamma delta times the determinant of lambda. Right? So this is a way of defining determinants. As you use an antisymmetric tensor, you take the product of the matrices to this up to the in the same number as there are indices, and this is the determinant. You can see various things. So if lambda, you see lambda transpose. Let me write that out in indices. This means eta. So let's take eta with downstairs indices. Downstairs indices go with lambda twiddle, right? So eta mu nu, and now let's do lambda twiddle mu alpha, lambda twiddle nu beta, eta mu nu is equal to eta alpha beta. And if I do upstairs indices, then of course I have lambda mu alpha, lambda nu beta, eta alpha beta equals eta mu nu. From these equations, you can take the determinant. The determinant of a product of matrices is the product of the determinants. Right? So the determinant of this equation, if we take the determinant, we get determinant of lambda squared. Determinant of eta is -1. Determinant of eta is -1. So det lambda squared is 1. So det lambda is plus or minus 1. Okay? And so when we come down to see the epsilon, we see there are some lambdas which leave epsilon invariant and some lambdas which change its sign. Okay, so epsilon is called a pseudo-tensor because of that, because a pseudo-invariant tensor, because it's invariant under only the Lorentz transformations with determinant 1. Okay. What's the time? I think I will, yeah, let me finish this little section. Now, what's the punchline? The punchline is the following, that we start from these equations. Let me, I'll write them in this form. Okay, and the punchline is that these equations are the same are in any coordinates related by a Lorentz transformation. Okay, so if we transform x to x prime, j to j prime, f to f prime via Lorentz transformations, then 1 and 2 are invariant or are unchanged. Okay, so let's see why that is. Well, obviously, if I just had one index on the left and one on the right, when I do my Lorentz transformation, this transforms to lambda, this to lambda, and I can cancel the lambdas because they're invertible. Here I have a lower index contracted with an upper index. Okay, so we have things like, but any vector with a lower index contracted or summed with any other vector with an upper index. Okay, if I work this out, the lowered index goes with the lambda twiddle. The upper index goes with the lambda. Lambda beta alpha u beta lambda alpha gamma v gamma. Right? That's the primed transformed vector. But now you see I've got lambda twiddle multiplying lambda. So, and lambda twiddle lambda is 1, is delta. So this equals u beta v beta. So whenever you have summed indices, they don't transform at all. Okay, the transformation of the lower and the upper cancel because one goes with lambda and the other goes with lambda twiddle, just as we saw over there. So you can just forget about these indices. Those are invariant. And likewise here, you have 3 summed indices. Okay, they don't transform at all. Then we have 1 free index, but that goes with the lambda. It may give a det, but that doesn't matter anyway because the right-hand side is 0. Okay, so in other words, the same equations, and let me just write it out in more detail, i.e. if f alpha beta of x and j alpha of x. Just to warn you, when I have functions of the coordinates, I may or may not put the indices here. This x really is x mu, but I don't want you to think of this as a tensor index, right? This does not transform. It's the argument of the function. All right? These are the indices which transform. So if I have some fields which are functions on space-time and currents on space-time, and if these two are solutions of the Maxwell equations, then f prime alpha beta of x prime, right, which is equal to lambda alpha lambda beta mu nu f mu nu of x. Okay, so it's very important to realize the argument of the old field strength is the old coordinate. The argument of the new field strength is the new coordinate. Okay, so this function, which equals that function, and j alpha prime of x prime equals lambda alpha beta j beta of x, are also solutions of the Maxwell equations. Okay, so imagine you've got some solution. It's a traveling wave of light, it's a charged particle with its electric field, it's a coil with a magnetic field. You have some solution. You know the charges, the currents, the fields, and then you change the coordinates in this way. Okay? Then you get new fields, and often, even if you just had an electric field before, now you have a magnetic field, because these matrices will mix up the electric and magnetic fields. So you had some components of F just in the electric directions, but you did some rotation. Obviously, that's going to push these into the other direction. So out of electric fields, you get magnetic fields, and vice versa, right? And out of static charges, you get currents. So the new fields, the new currents, also solve the Maxwell equations. Okay, so this is a huge symmetry that I'm free not only to do rotations, I'm going to be free to move at any constant speed. All of this assume the lambdas are constants, right? This is constant, i.e. independent of x, but that is the symmetry of the Maxwell's equations. So I think let's have a break, unless any questions now, and then we'll come back. Yes?
I have a question about yesterday's tutorial.
Oh, sure. I wasn't there, so you'll have to explain.
At how the electric field from a parallel plate transformed.
Okay.
And then we found that it looked like what we expected to, and then we looked at how F mu and U transformed.
Right.
And we said because they were the exact same, that it was the same thing.
Right.
Well, my question is, how does that mean that it works for every electric field? What if your electric field is made from something else?
Well, this shows that it doesn't matter what it's made from. Whatever field configuration you have from whatever current distribution, if you've solved the Maxwell's equation in one coordinate, and then you go to a different coordinates which are moving, you will get the corresponding solution of Maxwell's equation.
No.
Why no?
So the point of the exercise was to show that, like, because your solutions transformed the same, they were the same solution.
What do you mean by transform the same? Okay.
So we looked at a parallel plate.
Yes.
And then we figured out what the E and D fields were and how they Lorentz transformed.
Good. Okay.
And then we looked at F E and U, and we figured out they transformed the exact same. So it makes sense that your E and B fields are in F E and U.
Yeah, I'm not really understanding. Sorry. Why don't we discuss this in the break? Are there any questions about the lecture? Yes.
In general, just because the anti-symmetrizer of a tensor vanishes doesn't mean the tensor is symmetric, right?
No, okay, so for a 2x2 tensor, if the anti-symmetrize, for a 2x2 tensor, if the symmetric part is 0, then it's antisymmetric, and vice versa. If the antisymmetric part vanishes, it's symmetric.
I mean for any arbitrary rank tensor.
Right. So this is to do with the, what is called a symmetric group. And the general statement is the following. You use something called Young tableau. You heard of those? Okay. Young tableau. Okay. So let's say so what's the idea of Young tableau? Young tableau is to help you understand the different components of any objects under the group of permutations, which is called the symmetric group. Okay, so if we have two objects, we can put them like that. Okay, and then by definition, this represents a symmetric tensor, because I can replace the left and the right. Okay, or like this. This is an antisymmetric tensor, and there's a rule that let me see. Yeah, let me just see. Yeah, so let me say it the following. What's the idea of Young tableau? So you imagine every index I. So you have some object with some number of indices, right? If you've got only one index, that's a box. If you've got two indices, well, it could be symmetric or it could be antisymmetric. Okay? And so this represents the symmetric, and this represents the antisymmetric. And the rule of Young-Tableau is that you construct all structures like this. I'll show you what the general idea is. So this guy is symmetric. This guy is totally antisymmetric. But in addition, you have this guy with 3 boxes. Okay, and so that means it's symmetric under these 2 indices, but antisymmetric under those 2. Okay, and that's all you can do. So with Young-Tableau, you're instructed to make anything out of boxes of that character. Okay. Now let's say you go to 4, I, J, K, L. You'll have, again, this guy, then you'll have this one. Okay, then you'll have this one, 3, 4, and then you'll have this one. Okay, so what's the point of these diagrams? Look a bit silly, okay? Now, the first point of it is it immediately tells you how it breaks up under the group, under the symmetric group, the group of permutations. Very conveniently, it allows you to calculate how many components there are very easily. Okay, so if you have n values of I, if your index I takes n values, you have n, and this gives n. Okay? Here, the rule is, gosh, this is a clever rule. Okay, you write this guy down, and what you're supposed to do is the following. I'll write the boxes a bit bigger. Okay, so there's n plus 1, n plus 2. But then when you go down this way, you do n minus 1, n. Okay? Now, obviously, if you had too many of these, you're going to hit 0. So you can't, and that's the case where you have a completely antisymmetric object. Okay, so let's say we had 4, 3, 2, 1 for an index that took 4 values. This would be the epsilon symbol. Okay, and then what you're told to do is you draw these hooks. So there's a hook, comes in from the right, and it goes down. So I can draw hooks in many ways. I can draw this one, and this one, and this one. And so here, I draw this hook, and this gives me, let me see. This gives me n plus 1 over 2. Yes. I take the product of all the boxes. The rule is you take the product over all the boxes divided by the number of hooks. Number of components equals product of all the boxes over number of hooks. Okay, so in this case, there are 2 hooks. I can take both of them or one of them. So there's 2. That's why there's a 2 here. Okay. So if we do this one, we get, here I have n plus 1, n plus 2. Then I'll have 3 hooks. Sorry. It's actually it's the product of hooks. 3 times 2 times 1. Sorry, it's the product. The product of all the boxes divided by the product of the hook. So this is a hook going through 3 boxes, 2 boxes, 1 box. Here, I take n minus 1, n minus 2, divided by 3, 2, 1, etc. So if you look in a group theory book, it will tell you how things split up in this way. And what you should be able to check is that you say, let's say, in this case, I've got n plus 1 over 2 from this guy. This is n minus 1 over 2. Notice the sum of these 2 things is n squared. We've got 2 index objects. It should have n squared components. This is splitted up into the symmetric part, which is this many components, and the antisymmetric part. And I guarantee that if you draw any diagram you like and use this rule, You add up all these things, they will always add up to n squared, n cubed, n to the fourth, etc. Okay, so that's how it's designed. But yes, you're right. When you go beyond two index objects, you have many different components defined by their symmetry. Yeah.
But if you act with the epsilon tensor on anything that's not totally antisymmetric, it will still vanish, right? Because you have
No.
some...
I mean, if I have alpha, beta, gamma, delta acting on some matrix,
Yeah.
right? Obviously, this is going to be 0 for the symmetric part of the matrix,
No,
but it'll give me the antisymmetric.
I mean, if you act with it on one of the objects in the Young tableau,
Uh-huh.
then any object
Oh, something like
that's
this.
partially symmetric. So under the two indices that it's symmetric, it will die with.
That is true.
So anything. So
That's correct.
So any matrix that you apply.
Yes, if this one is symmetric and some other matrix is antisymmetric and doesn't matter about any other indices, then this must be 0 because it's equal to minus itself.
Okay. Yeah.
So contractions between symmetric and antisymmetric objects are always 0.
Okay. So. Okay.
I have a question that's not about the symmetries.
Okay.
Well, I guess it is indirectly. But so in this last part, when you're talking about how solutions of Maxwell's equation give rise to other solutions via
Yes.
transforms,
Yes.
Your statement about question 2 prime here, equation 2 prime,
Yes, this one.
saying that if you look at all of the primed variant,
Right.
it's not a problem even if you've got a negative determinate Lorentz transform.
No, because there's nothing here.
There's nothing here.
Yes.
You were saying earlier that magnetic monopoles would change that.
Ah, good point.
So does that mean, like, if we were to entertain the idea...
That's a good point. Yeah, so this would be electric and magnetic current. Yeah, that's a very good point.
Would you have to transform differently?
Exactly. So it would be saying that this equation would not be invariant under Lorentz transformations with determinant -1. That's correct.
So is that why you might conclude? I mean, obviously it's
Well,
but
you know, it's an interesting argument. It's an interesting argument. Let's think of examples of lambdas, okay, which have determinant -1. So what is lambda? Lambda is a 4x4 matrix such that I've got to have this lambda eta lambda equals eta, or lambda lambda eta if I write it this way. Okay, so one trivial example is the identity matrix. That's not going to leave eta invariant. Another one would be time reversal, where all I do, so this is saying CT prime is minus CT, and then X prime equals X. Okay, so this is time reversal. And that has determinant -1. So indeed, the equation written in this form would not be invariant under time reversal unless, okay, let me think. Yes, unless the following. You see, we always have to decide what is the transformation properties of J. So is J supposed to just transform as lambda? Or do we need something else? Okay, and you might say, no, I don't want to do that. I'm going to put a determinant of lambda in here as well. Right. And I think you can do that.
then I think if you're saying that just the magnetic current then has an extra determinant, but the electric one won't.
Exactly.
All right.
Exactly. So the statement would be that the magnetic current the electric current is a vector. Magnetic current is a pseudo-vector. Now, such things occur. I mean, even in classical mechanics, angular momentum is not a vector because, so if x goes to minus x, velocity goes to minus velocity, but angular momentum involves v cross x. right? So L is mv, the angular momentum is mv cross x. So if these two guys both reverse, this does not. Okay, so it's a situation similar to that. So you have to you may have to define vectors and pseudo-vectors, which transform differently according to whether the determinant was positive or negative. You can't get mixed up because these two components of the Lorentz group are disconnected. So if the determinant is 1, if det lambda equals 1, you can do all of those transformations. They're completely disconnected as a space from the component satisfying this. And so I think you're free to just define your transformation laws on the two spaces separately. So I think you actually won't get into trouble when you do that, but I must admit I haven't thought it through. But that's a good question.